This provides the basis for a useful notation. This big delta carbon-14. Big delta carbon-14 differs from the little delta that we use for the other isotopes because the big delta is normalized to the minus 25 per mil number. And in a lot of biogeochemical investigations, you will see reported not the radiocarbon age, but this big delta 14C. This is extremely useful because in a lot of investigations of natural materials, we're looking at some mixture of crap. I mean, you take organic material from a marine sediment, and we know it's a mixture. There's all kinds of stuff in it. The radiocarbon age in years is meaningless. We can measure the amount of carbon-14, and we can use that carbon-14 signal in lots of ways, as you'll see. But it's very complicated and quite unuseful if we think about it in terms of years. It's much better to have a notation like we use for the stable isotopes and to apply it to carbon-14. And the number that we use is this big delta. And it's useful, as you'll see right now, I hope, in a very nice way. If we look at carbon isotopes in food webs, we know that there's a respiratory fractionation. You eat some carbon, it gets involved ultimately in the tricarboxylic acid cycle. You decarboxylate acids in the tricarboxylic acid cycle. There's an isotope effect that favors the respiratory exhalation of carbon-12. So the biomass we build is heavy relative to the food we eat. So you go along, and from one trophic level to another, there's an enrichment in carbon-13. The enrichment that we would see for carbon-14, little delta carbon-14, is twice as big. If, on the other hand, we plot big delta carbon-14, it's flat because it's all normalized to minus 25. This means that big delta carbon-14 looked at, for example, in a food web, is a beautiful measure of the isotopic the carbon-14 abundance in the source. And it's unaffected by trophic effects. You want trophic effects? Use carbon-13. This measure of carbon-14, the big delta, is very, very useful in many biogeochemical applications. Oh, yeah, and here's the slide I promised. Here's this back calculation of the abundance of carbon-14 in atmospheric CO2. It's pretty shocking. It shows you that 40,000 years ago, there was twice as much carbon-14 in the atmosphere as there is now. This is a really big variation. And it's an important factor in keeping in mind in computing ages, I should say. Libby got unlucky. For the sort of multiple thousands of years that he had available in his artifacts, there was this, dated artifacts, I mean, there was this sag in carbon-14 abundance. So he came up with a slightly low estimate of the half-life. If that had been absolutely flat, his estimate of the half-life would have been correct. But he was undone by this natural variation, which we now know about. It means, by the way, that radiocarbon dating for the past 2,000 years or so is a really tough business. Now let's talk about measurements. The measurement of carbon-14 was originally carried out by counting radioactive decays. You sit there and you count the beta particles, and you can get an estimate of how much carbon-14 is in the sample. From a modern sample, you get 8 disintegrations per gram per minute. It means, by the way, that in our bodies, there are hundreds of disintegrations per minute. You don't feel them. We're sitting here. We're decaying. And these are, I mean, literally decaying. Carbon-14s are turning into nitrogens, happening in our nucleic acids, screwing up our genes as we stand here or sit here. And it goes on all the time. It's not, highly damaging. The range of the particles is about 1/10 of a millimeter. But it's a process that is useful if you want to detect carbon-14 up to a point. As you see, if you want to get a 1% counting error and you have 1 gram of carbon, it's modern, you can achieve that precision in 21 hours. But if you had, more realistically, only 1 milligram, and it was an old sample, you'd need a long time to get good precision. So the bottom line is what you see. Waiting for atoms to decay is very inefficient. The big advantage of mass spectrometry is that you don't have to wait for it to decay. You measure all of the carbon-14s that are there. The difficulty with that is that you're trying to measure an isotope ratio which is tiny. The modern carbon-14 abundance, expressed as a ratio, is 10 to the minus 12. The ratios that we measure easily for the stable isotopes are like 10 to the minus 2, 10 to the minus 3, worst case 10 to the minus 4. If you're building a really good isotope ratio mass spectrometer, you brag about its abundance sensitivity, how much stray ion current appears only 1 mass unit away, and if the abundance sensitivity is 1 part in 10 to the 6th, you advertise it. I mean, this is a big deal. That's still 6 orders of magnitude higher than you would need to detect carbon-14 at natural abundance. The other thing is that in order to get a measurable signal when it's only 10 to the minus 12, you have to have a huge carbon-12 signal in order to see any carbon-14 ion current in your spectrometer. And that means, you're really overloading some poor ion optical system, putting into it this fire hose of carbon-12 and wanting to measure this little trickle of carbon-14. So it's a big challenge. These are illustrations that actually pertain to deuterium measurements. When we started to measure deuterium isotope ratios in the presence of helium carrier gas, we had a problem pretty much like this, where here's, let's say, mass 2, mass 3, mass 4. If you just had low abundances of those 3 ion beams, 2, 3, and 4, you can resolve them very, very easily in a mass spectrometer. Separate mass 2 from mass 3. Heck, you could do that with a bar magnet. The problem is that in a GCMS system, you've got a huge beam of helium, so that you wind up with the mass 3 beam looking like this. And that arises not because your resolution is poor. The resolution of the mass spectrometer is very good. You can separate it easily. But you've got underlying mass 3 scattered ions from the big mass 4 beam. Because they're scattered, they don't have exactly the same energy as the main beam, so it's easy to get rid of them. You just use an energy filter and you can measure the deuterium isotope ratio very easily. That's the technique or the trick that's used in hydrogen isotope ratio GCMS. You got to do a little bit more than that in the case of carbon-14, but it's the same kind of problem. The first problem that you have is that there are, or the essence of the problem, is that there are non-scattered ions at mass 14. The champion, of course, is nitrogen-14, which is just a tad bit more abundant than carbon-14. It's the most abundant nuclide in the atmosphere. It's everywhere. And if you try to build a system based on positive ions detecting carbon-14, you're doomed to failure. Really smart people worked on it for decades and never made it work. Then it was recognized that N-, the negative nitrogen ion, is unstable to say the least. As you can see, its lifetime, that's the E-folding time, is like 10 to the minus 14, 10 to the minus 11 seconds. So it's literally true that if you make a negative nitrogen ion in the source of your mass spectrometer, it decays before it can even get to the detector. So you don't have to worry about nitrogen if you use negative ions. So that's the first thing we do in the mass spectrometry that's used to measure carbon-14. We use negative ions. That solves the nitrogen problem. Hallelujah. The difficulty is that by making ions with more electrons, you stabilize these polyatomic ions, 13CH and 12CH2. Give them more electrons, they can hold together better, they're more stable, and even though they only result from adventitious water that's available on the surface of your sample when you're making ions, they're abundant enough that it's a major problem.